What are limits? You might have heard what limits are before, but essentially it's just the y value that a graph is approaching as x is approaching a certain value. So as we can see on the graph right here, y equals x squared, the x value approaches 1, and with that, from both sides, the y value also approaches 1, so therefore the limit as x approaches 1 of x squared is 1. Limits follow the basic rules of algebraic manipulation. Like, for example, here you can split apart the limit and add them, multiply them, divide them. You can also take out a constant out of the limit and just evaluate the limit of the function itself and then multiply by the constant. If your function is raised to the power of n, you can take that out of the limit as well. So yeah. Now let's look at Heave-Side functions. Alright, essentially what a Heave-Side function is that the limit as x approaches a from a certain value from the positive side is different from the limit as x approaches a from the negative side. So right here we can see that the limit as x approaches a of f of x is equal to a 1 on the right side. The limit as x approaches a for f of x from the left side is 0.1. So because these two values are not equal, we can say that the limit as x approaches a for f of x does not exist. Now, let's look at evaluating limits algebraically. There are a lot of techniques to doing this, but let's run through the easiest ones first. Okay, so if a function is continuous, in which it means that it has no discontinuities, or there are no issues when you just plug in the value of the limit into the function, then you can just plug in that value, right? For the top example, the limit as x approaches 3 of x squared plus 4x plus 3, you can just evaluate to 24, since x squared plus 4x plus 3 is a polynomial function. Alright, but sometimes we're going to have issues when we plug it in. See, we can see that when we plug in t approaches 0 into square root of t squared plus 9 minus 3 over t squared, you can see that we're going to have a divide by 0 error if we just do that right away, right? So what we have to do is multiply by the conjugate of the numerator to get rid of the radical in the numerator and the t squared term in the denominator. Once we do that, we can see the plus 9 and the minus 9 cancel out, the t squared and the t squared cancel out as well. So we just end up with 1 over the square root of t squared plus 9 plus 3, and now we can just plug in 0 for that limit and just get 1 over 6. Sometimes we're also going to have to factor a limit. So as you can see with x squared plus 2x minus 3 over x minus 1, we can see that they have a common factor on the numerator and denominator. So we just cancel out those common factors, and now we can plug in 1 to evaluate to 4. If you have a piecewise function, you can also check if the limit exists at a certain point. So we want to find if the limit of x approaches 4 for f of x exists right here. So what you can do is recall the Heave-Side functions. We want to check if the limit as x approaches a from the positive side is equal to the limit as x approaches a from the negative side. So right here we can just check for the positive side. The positive function is square root of x minus 4, so we can just plug in our 4 and we get 0. We can do that from the negative side as well, and we just plug in our 4 and we get 0. And because these two values are equal, the limit as x approaches 4 f of x exists, and it actually equals to 0. And the reason that we can just directly plug in 4 for these values is because as x grows very, very, very small amount bigger than 4, so 4.0000001, we can see that the square root of 0.00000 repeating 1 gets closer and closer to 0, so we can just directly plug in these values. As for the other side, we can also see that 2 times 3.999999 is a tiny bit smaller than 1. It approaches 8, so you can just plug in 8 for that value. So the value of the limit also approaches 0 there. Sometimes we're going to have to evaluate infinite limits, so when x approaches infinity. And right here, you can see that, like if we just plug in infinity for x, well, it should be like infinity over infinity, right? And that looks like it gets us -1, but it actually doesn't. It's considered an indeterminate form. Because the magnitudes of infinity are different, we can't cancel them out. Alright, so However, we can recall from rational functions that the leading coefficient of the numerator can divide by the leading coefficient of the denominator as long as the degrees of the numerator and denominator are the same. So we can see that we just have -2 over 1 is equal to -2. And because a horizontal asymptote is as x approaches infinity, we can just do that. However, let's formalize this in terms of limits, all right? What we can do is we can divide each term by the leading degree of the function. So we see the leading degree is x cubed, so we can divide each term by x cubed. And this is totally like legal in terms of math stuff to do, math manipulation, right? Now when we do this, we just get -2 plus 2 over x cubed over 1 minus 1 over x squared. The 2 over x cubed and 1 over x squared terms both approaches 0 as x approaches infinity, because the denominator actually grows without bound. Alright, so now we can just plug in these values of 0 for 2 over x cubed and 1 over x squared, and we get -2, the same answer as before. Now, let's see what we want to do the limit as x approaches infinity of 4 over 3 to the power of -x. What we can do is we can take the negative and put it inside the base, and we can see that we have 3 over 4 to the power of x. And since the base is greater than 0 and less than 1, we can say that the denominator grows faster than the numerator, so as x approaches infinity, so the value of the limit is approaching to 0. Now for our last part, what are some rules for continuity? Alright, so the rules for continuity is that f of a exists, the limit as x approaches a of f of x exists, and the limit as x approaches a of f of x is equal to f of a. Let's look at this first part. Basically, we just want to say that for any arbitrary point on the graph, there is, like, the function of that point exists. So this just like eliminates any chances for like asymptotes or discontinuities and things like that, right? Because we're just saying every point on the graph must exist. Alright, and now for the second part. The limit as x approaches a of f of x also exists. So essentially what this means is that the limit as x approaches a from the positive side and the negative side of f of x must converge to one point, which, like we said before, eliminates Heave-Side functions. So like we can see right here with the blue, as x approaches a from the negative side is not equal to x approaches a from the positive side. And we can see there's a visible discontinuity there between those 2 points. So that's what the second idea covers. Alright, so now we should consider the third idea, which is that the limit as x approaches a of f of x is equal to f of a, alright? So essentially what this means is that it considers jump discontinuities, like you see that blue dot on top, it considers that discontinuity, and it says that the graph is discontinuous if it has a jump discontinuity, right? The reason that this has to be said is because the limit as x approaches a of f of x can still exist if a is just a tiny bit bigger, and if a is just a tiny bit smaller. The values will still be approaching this y value of 4, right? But right here, we can see that it clearly has a jump, right? So where f of a exists at this blue dot, it has to be a discontinuity, even though the limit as x approaches a of f of x exists, right? So that's just something else to consider. Now let's go through a couple of, these are just going to be some practice questions for you to do in case you feel interested in doing it. And yeah, honestly, that's it. Thank you for watching the video.